Welcome at the European Industry and Energy Summit 2021 at the side event of the Field Lab Industrial Electrification. Welcome to the audience present here on the location. Welcome to the digital viewers at home. I'm Josefa van Kollenburg. I'm the director of the Field Lab Industrial Electrification. And I will tell you something, first of all, about the Field Lab, and then we will have a very exciting program for you. It's a full program, so let's quickly start.
Industrial electrification.
And first I will say the Field Lab Industrial Electrification is founded by 5 founding partners: Port of Rotterdam, Innovation Quarter, TNO, Delta Links, and FME. And before I will give a nice presentation, I will shortly show a video to high-levelly tell something about our Field Lab.
Industrial electrification is an important sustainability option for the process industry in Rotterdam. It is important for investors and end users to see electrification applications tested on a large scale. Otherwise, promising technologies cannot be developed and implemented. The Field Lab Industrial Electrification will therefore provide a safe and scalable test environment, uniting ambitious global players to create a new, cleaner process industry, helping to fulfill the potential of the energy transition in Rotterdam. Join us.
Well, indeed, join us. The headlines tell enough. We see articles in the newspapers about CO2 emissions that need to go down, the climate goals, IPCC report, CO2 taxes, coal plants that will be closed or that are closed. It's all about CO2 problems, and you get rather CO2 exhausted. But there are a lot of solutions already existing, but not being put into practice yet. And I think if we look at it differently and rethink it, that we talk about growing a new green sustainable industry sounds better and gives more energy than talking about the CO2 negativity around it. And there are a lot of technologies already existing, thinking about heat pump, e-boilers, but also a lot of technologies that still need to be tested. And there our Field Lab comes into place, because we are at the beginning of a new industrial revolution, and you can all join it. So let's do that together. The Field Lab Industrial Electrification unites ambitious players around the world to create a cleaner process industry and to follow the final goal of reducing the emissions. And we want everyone to join us, of course. If we look at the region here, we have 2 challenges. One is the climate challenge, and if for the high energy industrial section here in the port and around the port, we can lower down the emissions, we can achieve 20 to 25% of the national climate goals for CO2 reduction. But we also have an economic responsibility and a challenge, because the new industry, and a greener industry, also asks for new types of jobs, new education programs, and also keeping the human capital aspect in the region and not losing all these brilliant minds to other countries. So that's an important thing. And our main mission of our Field Lab is that we want to reduce the CO2 emissions. And we will do that by gathering the knowledge of our founding partners and helping to solve very complex projects and studies, and also offering the equipment and the technologies to do so. But scaling up the innovation is a major step. Coming from a pilot to a final implementation on an industry location is tricky. And it needs an end user to be connected with the technical provider of the new technologies. But what you see is that the current industrial end users don't have the facilities to test it at their own premises, because they need to adjust their infrastructure. and they need to see the technology being proven in the right conditions, but also things like security, that the fire extinguishers can be there in time, or the fireman. You need permits, and that makes it very difficult to connect these two important partners together. But moreover, there is a location needed, a practical location where the industry can see these Power-to-X technologies work in real life and see if it really fits their company. And there, the field lab comes into place, because we see ourselves as a driver of the cooperation in this new value chain, because a new value chain will be needed to go to the new green industry. And then it doesn't work. Intended partners of our field lab are a few. Of course, the industrial end users who want to partially or fully electrify their processes, but also the technical innovators, the companies that have these nice ideas and they want to test it at these end users. But moreover, you also need to have the energy companies and the network administrators to work together on this. I think I need some help with going to the next slide. Now, if you look at this slide, you see on the right the intended projects that we want to have at our field lab, industrial electrification. That if you follow the former steps on the right way, it is easier and you can faster achieve these bigger projects. And the most part of lowering the emissions is by electrifying the industrial processes, and we call that a Power-to-X technology. And the ones that we distinguish are the power-to-heat, the power-to-chemicals, and the power-to-hydrogen. And that changes the fossil-driven industrial processes into green-driven, so green energy or green molecules. And ending up in these nice projects, of which we already have a few. Next slide. The field lab consists of a solution center, where we can do feasibility studies, where we can help in law, some difficulties with laws, with having the right permits, subsidies, but we also give workshops. We have nice presentations or side events like this one to connect the industrial end users with the technology providers, but we do more. The next phase is that we have a test facility where you can test the technology on a TRL 4 to 6 level. And after that, it can be possible to go to a demo plant. But all these steps are interconnected with each other. So you can go from the solution to the pilot center, to the demo, and back again to the drawing table if some extra research is needed. But an important step is our location that we will open next year, and we recently signed it. So I want to just give you a small view how that will look like with the next video. And there should be some very nice classical music behind it, but I will talk you through it. This will be the hall where the 3 lines will be located. It will be 3. We'll quickly show you the lines after this. We will also have our office over there. So we started at the RDM location, but we will move to this location at the premises of Plant 1, and that will be next year already. We will have 3 lines. One is a power-to-heat line, as you can see here. So it will either have hot air or hot water or steam as a result, and all these different parts can be interconnected. Other machinery can be put in. There's also the possibility to have an extra container. We will have also an indirect conversion of CO2 line and a direct conversion of CO2 line, but we changed that scope a little bit to an electrolyzer part because the rest of that line wasn't market ripe yet. So we chose to start with this. Well, we have a lot of technologies, as you can see here, that can be implemented. And we always say, and if I can go to the next click, because this one isn't working. Yes, the best technology doesn't exist, but what we do with our field lab is create the right learning conditions to have the right technology fit for your company. And that is what we will be doing today with a case presented by Ducor. And Rens van Leuken will shortly present that complex case that they have with an electricity business case. You can also contact us if you want to have the same case and event as well, but also if you want to know a little bit more about our field lab. But if you look at the... it's really not working. At the program that we will have, I will quickly give the word to Rens. I see that a different timing is given here. We will have a few pitches. You will see the names here. They will have 8 minutes. A countdown clock will be shown on the screen. The 8 minutes are for the pitch, and I have the pictures here already available, but there's also including questions. So be aware that it's a timely thing. But after that, we will have a nice presentation by Robert Geurts from the province of South of Netherlands, and he will talk about industry policy and innovation. And then we will have a table talk to decide which pitch is the winning pitch. So I will quickly give the word to Rens from Ducor. I hope it works for you.
Well, thank you very much, Josefa. It's really a privilege to stay on this stand and present our case. My name is Rens van Leuken, Operations Manager for Ducor Petrochemicals. I will give a brief introduction of Ducor, give an overview of our environmental footprint, and then I will go to our case study that is related to electrification. Ducor Petrochemicals is owned by Bazan Group, an Israeli company. It's owned already. Ducor is owned already for 10 years by Bazan, and Bazan has oil refineries, crackers, and polyolefin plants in Israel. We, as Ducor, are a rather small company. We are focusing on long-term partnerships with our clients. We anticipate on market trends and also do our own innovation on polypropylene products together with our clients. A very brief overview of our process. We have a nameplate capacity of about 180 kilotons a year. Propylene is delivered by ship or by pipeline. We have 3 independent reactors. And in the reactors, polypropylene powder is produced. The reaction is exothermic, so quite some heat comes free with the reaction. And reaction powder goes to the extruder section, and at the extruders, a granulate is produced. And the polypropylene granulate is about 3 to 5 millimeters in size. This technology is based on Novolane, and some words on polypropylene. It's a rather well-known plastic, easy to recycle. And an average household in the Netherlands owns about 100 kilograms of it. And it can be in automotive applications, packaging, food packaging, artificial grass, etc. And our production is able to produce 3 product families, homo, random, and copolymers. And from these 3 product families, we produce about 40 different grades that are used by our clients to produce end products. So we are fully business-to-business focused. Some information on our environmental footprint. Here some electricity and steam figures are depicted. We have electricity usage on a yearly basis of 66 gigawatt hours, which is close to a power of 8 megawatts, and an average steam consumption of 5 tons an hour. Well, the cooling water gives an excellent opportunity for electrification and for energy optimizations. The duty of the cooling water tower is about 24 megawatts, and it can be used with electrification to reduce our environmental footprint. And especially on our indirect footprint on CO2, what you see from electricity and steam. That's 85% of our total CO2 footprint. And when we would be able to reduce our steam and electricity consumption, or maybe only the steam consumption already, then we can have a major impact. As Ducor and Bazan, we are fully committed to have a significant impact on our environment and to reduce our footprint, not only by optimizing our current processes, but also by strategic projects related to chemical and mechanical recycling we just started. And we intend also to acquire or start new businesses around mechanical and chemical recycling. But then the Ducor case. Here's some highlights. We have steam imports at 18 bar G, on average 5 tons an hour. And some main consumers are a splitter reboiler, 1.4 megawatts duty, average steam flow of over 2 tons an hour, and the steam is injected in water to maintain 90 degrees Celsius in a water circulation loop. Well, 40 years ago, this was engineered and built. Nowadays, we would do different, but that is the current situation we have in our plant. And then we have a propylene heater, 0.7 megawatts, in operation 30 to 40% of the time in a year. And steam consumption there is about 1 ton an hour. On the other side, we have quite some excess heat in our extrusion section. So the granulate is cooled down just after the die in the extruder with cooling water. The cooling water heats up from 54 to 60 degrees. And then that cooling water in circulation is again cooled down with cooling water central in the plant. Every line has such a system, and the total duty is about 3.5 megawatts. We did some engineering on a conventional heat pump. That is on the next slide. And it turned out that the business case was not directly feasible for this case. So with the conventional heat pump, we used the excess heat in the granulation section to have a new water recycling loop of 90 degrees C. That water can directly be used in the splitter reboiler, and with a new heat exchanger for the propylene heater, we can also use this water circulation to replace the steam used for both applications. So the question for this case is how to optimize this situation so we can make a feasible business case out of it. And that was the question that is central, is the question for this business case. And I would like to hand over to Josefa, I think, and I'm very curious on the 4 pitches and the ideas they come up with.
I think we first, let's check if there are some questions maybe here from the audience that can give some extra input for the pitchers as well. Anyone has an extra question for Rens about this specific case of Ducor? Marco.
My name is Marco Kirstein from FMA and also a participant in the field lab. It's not really a question about the business case you're referring to, but You told us that the process has been installed 40 years ago, and I was wondering, why is Ducor changing the progress at this time? What's your motivation to get into contact with us and make changes to the process?
Well, the main reason to start this project and this engineering is to reduce our footprint and to have less impact with our production for the environment and our planet. So that was the main reason to start the project. Well, and then we have a business case with a payback time of 7 years, and that's not really an interesting business case. And we see from this business case that quite a lot of infrastructure is required. Also, for example, the replacement of a heat exchanger and quite some piping, additional piping and new infrastructure that leads to an infeasible business case. But that was based on a rather conventional heat pump that's already available and could easily be installed. But developments, especially related to heat pumps, well, our focus point also for the field lab. And that's why we reached out and, well, we had a discussion also earlier this year. How could we benefit from each other's interest? And that's why we set up this case.
Thank you, Hans. Any other questions or remarks? Yeah, Marit?
My name is Marit van Lieshout. I wondered, I got a bit nervous because I'm afraid that I misunderstood the case. The water loop is already there, or I thought it was new?
What? The heat pump in the latest slide isn't there.
But the water loop is already there for both?
No.
The water loop is new for both?
Yeah, for the propylene heater, the water loop is completely new. And for the splitter reboiler, there is a water loop at 90 degrees C, but it's now by steam injection. So there is steam injection in the water loop to maintain the temperature at 90 degrees C. But well, that's a design from 40 years ago, and that wouldn't be a design right now.
Don't be nervous. It will be okay. No worries. I think it's time that we give the floor to our pitchers. Thank you so much, Rens. We will see you at the table discussing the pitches at the end.
Yeah, thank you.
Thank you so much. Have a seat. The first pitch will be here on location as well. We will have 2 pitches via Zoom. I would like to invite René Waggeveld from Blue Terra to give his pitch and why Ducor should have another discussion with you afterwards, because you have the solution to their problem, I hope. Good luck.
Thank you very much. Rens, thank you very much already for introducing the case. I think it's an interesting case also because this is for you a unique case, but not for the industry as a whole, because we have a lot of installations that are ages and at least decades old. So design from the past is not the design of today. So this one might be a good example that other companies would experience as well. My name is René Waggeveld. I'm working as a consultant for Blue Terra, and we try to also play our role in the energy transition by giving advice to industrial companies how to come to a more sustainable energy system. Today's case is about recovering waste heat. That's at least how I defined it. Rens has already given some insight into the case, so I can do this shortly. What is, I think, very good to notice is that on this site, there's even more waste heat available than the current steam demand. So there's excess heat, and this excess heat is, as Rens already explained, partly from the exothermic reaction and also partly because of the friction that's caused by the extrusion process. The extrusion is happening at a very high temperature of about 220 degrees. So waste heat is available also at that level initially. And the requirements for the heat, currently steam is used, and that's what Rens already explained, because that is how it was designed in the past. If we really look into the two heat exchangers where the heat is required, we see on one side a cold propylene heater, where propylene is heated from -40 to 10 degrees centigrade. So I could easily even say this is not a heat requirement, but this is a cooling opportunity. So companies could be happy to have such a very cold stream to use it for cooling in their processes. And the other one is the splitter reboiler, which operates at around 90 degrees, but also steam is used nowadays for this case. We made a hot and cold curve for this because we got some information from the site about the available heat and cold streams. In this graph, you can see on the x-axis the heat and cold streams in kilowatt, and on the y-axis you see the temperature level of the heat and cold. And on the red line is the hot curve, and you can see that the amount of heat available at the high temperature even exceeds the current demand at low temperature. But this is, of course, direct heat from the granules. So before we dive into a heat pump, as a consultant, you always think, do we really need a heat pump for this? Or is there probably another solution? So if we check the level of the heat that's available in the granules, that's around 220 degrees centigrade. Of course, those granules need to be cooled rather quickly to the lower temperatures, and nowadays cooling water is used for that. 60 degrees cooling water, or 45 degrees, which heats up to 60 degrees. But if we try to make use of this very high level heat by using a heat stream of around 75 degrees and heat that to 95 degrees, we already have heat available at the level that we need it. Of course, this is really has impact on how the process is run today, and we still need the cooling to the temperature of 60 degrees later on. But it might be an option. Before we really need the heat pump, can we use the heat directly? And of course, if you compare it to the heat pump, this has a very high COP because you need only the pumping energy to circulate the water. And 95 degrees is the highest temperature required. For the polypropylene heater, we can even use lower temperatures. For us, next best is still the heat pump. I've also drawn the heat curve once more on the right side for this case. If we check it, we can still generate heat from 95 degrees centigrade to be able to supply heat both for the splitter reboiler and for the polypropylene heater. The heat demand in total is 2.1 megawatt, and we can, with a high temperature heat pump, and there are different suppliers already, so it's new, it's sort of high level, but it's available at the market, and there are quite a number of suppliers at this moment. Oxner, an Austrian company, is one of the possible suppliers of these kind of heat pumps. Frisotherm is one of them. There are 4 or 5 different suppliers of the high temperature heat pump that still deliver heat below 100 degrees. We made a quick calculation of the capex required for this case. That would be a bit less than 2 million. Of course, it also depends on, and Rens already mentioned that, how much do we need for the infrastructure. And if we looked into the savings in money, that's around 0.7 million euro a year. What's always important if you look into electrification is, do you have a grid supply? Is that large enough to supply the extra electricity for a heat pump? This one is not a very big one. It's like 0.4 megawatt as a max, but well, we need to know if the grid supply is sufficient for that. And to be ready in time, just 1 minute left. Conclusions from this pitch is there's ample waste heat available at this site, and I think that's not only at this site, but a lot of sites do have waste heat available, usually at a lower level, because it's from cooling water. We can use and really get the heat supply to the two heaters without any fossil fuel, so based on either direct heat or electricity. First of all, you consider the direct heat with the granules, and well, next best I would call it the heat pump. So that's well, our solution to the pitch, and I think it's a twofold solution.
And we have a few seconds left for questions. So, Rens, you have an urgent question that you want to ask?
It's counting down, so
Yeah.
don't know if we have time, and otherwise we will do at the end of the presentation.
You write it down? Well, is there a very, very important question that the audience wants to ask? I'm a little bit flexible with the rules sometimes, so... Willem.
My question was about... Sorry, yeah. Willem Haas bij Stork. My question was about the COP. I see always you have a COP 5.0. I see it also in living houses. But when we get to real world, this number gets dramatic down to 2.7, to 3.0. Also, why do you believe that this is 5 and even COP is not feasible? Also, how do you think this will be unfeasible, these numbers?
So your question is this high COP possible and really achievable? Yes, the 5.0 for this case, and also based on the cooling water temperatures, even on the low side. But we have a solution where more suppliers can supply this heat pump. And I think we can go up to 5.7, 5.8 for this.
Thank you. Well, thank you so much, René. Let's see if this presentation was enough to go into the next round. I want to ask you to take a seat again, and then we will go to our digital... Thank you. Oh, he's already there. Jacob Haverkamp from Haverkamp Consultancy. Via Zoom, you will be tuning in to give your pitch.
Thank you.
The floor is yours.
Okay, thank you. Can you hear me?
Yes, we hear you loud and clear.
Okay, I started time because 8 minutes is not very much, of course. Do we have slides on the screen?
You see the slides? Yeah.
I don't see them here. Okay, they are there. Thank you. Well, first slide, we can just my name and saying that I am looking for the best opportunity in this case, and then I would go to see slide number 3, just for the information. How does a heat pump look like? Next slide, please. Yes, so simple, some examples how heat pumps could look like. It's just for information, just for showing there are so many different ways of building heat pipes of heat pumps. So just to give you any idea. By the way, we're talking about the lowest one in the next slides. And first of all, I need to say that I understand the challenge and give a pitch about there were two challenges. How do we get a better payback time for a heat pump that we need? And what would be the second challenge would be how we avoid needing steam? Well, I would like to go to the next slide, please. That's about nothing. So let's go to the next one. And then we see the heat pump. I did some investigation about which heat pump we should select it in this case, and I found a heat pump with with lots of opportunities, and even the opportunities are more than we need in this case. But maybe it's good to show you that can use heat sinks or heat sources from, let's say, 20 to 120. And at the sink side, they can go to 165, and in the near future to probably 200 degrees, even producing direct steam, as they say. Well, that sounds like a miracle, but well, the future will tell. We have a few minutes more, so let's go to the next slide, please. And this is what I said already. You can see here the main issue is the compressor, of course. That's the main part of the heat pump. And on the left and the right side, you will see the opportunities what they can do. It's quite a lot. Then I would go to the next slide. That's the name of the manufacturer, which is, in my opinion, not really important for this moment. And then it comes to the most important slide of all. This is financial things. I did 3 simple calculations as I calculated a heat pump with even to come back with the other questionnaire, even a COP of 6.1, but I kept it, to make it easy, I calculated 6. And this is not what I calculated, but it's what the heat pump manufacturer says. And it is very high, and that's the real is rather simple. Well, because the lift between the lowest temperature and the highest temperature at the source and the sink side is very small. That makes it very easy for a heat pump that can, which is able to use higher temperatures. And because it's only, let's say, 30, 35 degrees to lift, then that's 45, sorry. And that makes it possible for having a very high COP. And when you compare it to heat pumps in houses, etc., don't forget the temperature all year long is the same continuously. So it cannot be compared to a heat pump in houses. Anyway, I calculated a price per kilowatt of 600 euros. So that means we have an investment of 2.5 million. But keep in mind, I calculated the heat pump for 4.2 megawatts. So using all the available heat from what has been set in the challenge. And that means at the same time that you won't need to buy any steam anymore. As I had to make a guess about the price of power, and I calculated 10 cents per kilowatt, so I could make a calculation of the gains and the losses. And then you see, so I have a very simplified calculation yearly saying that it is about 750,000 euro a year about the cost. But the gains is we don't have to buy any steam anymore. So there is some profit in not buying steam. And I calculated 35 euros a ton, which was also a lucky guess, I hope. And that makes at the right side, we see a first payback calculation of about 3 million. And when it comes to extra cost, you see that I have to go back to step 1 when you see that I calculated about $480,000 euros for doing setup, installation, etc., etc. So there is some budget in my idea. Finally, so yes, the need of steam will be excluded while using a heat pump. And yes, payback time could be lower than 7 years, even lower than 4 years, I think. So to make this close, I found out that I should have more financial information, especially when it comes to price from power and the price of steam. Well, that was an interesting one, I think. So maybe we could go to the next slide. Is there a next slide? I think so.
You still have 1.5 minutes left.
Yeah,
so.
Okay. As long as the slide is there, then
yes,
no
it's there. The conclusions and ideas.
And everybody can read and yes. So one of the things I found was please share data when you talk about investigated study. to make it easier for other manufacturer suppliers what they have to do. I was missing the price of power and steam to make to find out if the payback time would be feasible, and keep in mind, capex is not the only thing that makes the payback time. So that's about it. And there is half a minute left. Thank you.
30 seconds left. Can you read it? Yeah, oh, perfect.
I skipped 10 slides yesterday evening, so...
Well, you're in time, so there's still room for a question. Rens, you have a question for Jacob?
I have one question for Jacob right now.
Yes.
Thank you very much for the presentation. You presented a heat pump for direct steam. Can you tell a little bit more about the TRL level of these heat pumps?
Well, they're ready to market, and they already have been selling first projects, and it's a coincidence that the project will be installed in the Netherlands next year. And at that location, they will produce 130 degrees water or steam, whatever. And so yes, the product is there, and you can buy it.
Okay.
Okay, thank you.
Thank you so much.
There's much more information needed to convince that is this the best for you, but this is here how we start.
It's a pitch, so
Yes, it's
indeed,
a pitch.
let's hope you have the opportunity to go into the next round of discussions with Ducor. I want to thank you and the nice Christmas tree behind you. It's nice having you online, and I hope you can also join digitally the discussion later on. I will go quickly to the next pitch. Thank you, Jacob. The next pitch will be here live again with Marit van Lieshout and Amar Nikam from RHDAV. I will quickly shorten it, and SPIE. So the floor is yours.
Thank you,
Good luck.
Josefa.
And you have 8 minutes.
Well, 5, because we have 3 for questions.
Okay.
Well, we are already introduced, so I go dive head first, because we had 5 minutes. And all the previous speakers have been so kind to introduce all the things you have to know before understanding this topic. We started with a description of the case as shown here, and I just realized that we misunderstood a part of the description. We thought that the green part in this case is to be built if you want to realize this. And I realize now that only the part of the propane heater has to be built, and the rest is already there. Or that is...
Yeah, there is a water circulation loop over the splitter reboiler, and there steam is injected to maintain that temperature, yes.
Yes, and I thought the whole water system wasn't there. So that, but it's a slight change in case. First of all, I have to agree with the first speaker that if you can reuse the cooling water, if you can realize a kind of heat exchanger that gets the cooling water at a higher temperature, then that is the first thing to study. We assumed that there wasn't the water loop system yet, and that you had a technical reason not to do that to get the granules cold enough. Having said so, what did we do? We looked into this case and we thought, okay, why is this? What makes this case potentially expensive? Well, first of all, you have this COP of you have to heat the cooling water from 54 degrees to 95 degrees to get enough heat, as explained by the first presenter. That is a significant lift, and that requires quite a lot of electricity. Secondly, we thought, okay, you have to adjust your heaters. Apparently only one, but we thought both. And so we thought, okay, how can we improve that situation? So what we did was, okay, if we integrate the heat pump directly with the places where the heat is required, then you reduce the temperature lift required. So in the splitter reboiler, you only need 75 degrees Celsius. So if you have a heat of 80 degrees, it's more than enough to get the temperature in the splitter reboiler. And for the propylene heater, you only need 66 degrees. So, well, if you have the heat exchanger, you need a bit of a driving a temperature difference as a driving force. So if you have 72 degrees at the propylene heater, that would be enough too. And in that way, you can increase your coefficients of performance significantly, and without further optimization, and that is still really an option, we already get an average coefficient of performance of 5.7 for this configuration compared to the previous one with the water loop. And in addition, you don't, well, apparently the splitter reboiler is already suitable for water. We assumed it was only suitable for steam. And as you know, steam has has a far higher energy density. So we think that, well, still for the propylene heater, you need less adaptation since you have a similar size heat exchanger required. Now, what this means in terms of energy saving and cost, my colleague Nika Mamar will tell you.
Yeah. Thanks, Marit. Now we will go to the cost perspective of this case study. So here we have calculated that steam is imported with an average of 5.5 tons per hour, and this is, we have calculated that currently based on the steam energy consumption, it requires 1.2 million euro per year. And as Marriott explained the alternative case for the smaller heat pumps, we required only the electric energy, and we calculated around 1.3 million euro is required. So here you can see there is a lot of reduction in the cost, which will be around 0.9 million euro per year. Now we will go to the investment. For these smaller heat pumps, the investment cost is required around 1.1 million, but currently we don't know the exact site data, so it will be supporting ENI system, and the integration of this heat pump with the splitter reboiler and the propylene heater is excluded because of the difficulty of the data from the site. So you can see the total cost is very difficult, but we can estimate the total cost once we know the more detail from the site. And I can definitely say that the smaller heat pumps are cheaper than the water loop system, because the water loop system, what we have calculated, is required around 1.5 million euro investment. So the conclusion here is the alternative dual loop heat pumps has a lower energy consumption, has a lower capex, and has a better payback time. So I think I give it to Marriott.
Well, thank you. Apparently I used too many words to explain my misunderstanding, so we only have 1 minute, friends, for questions, but also from the audience.
Well, I was triggered by your remark that 2 heat pumps were cheaper than one larger. Can you explain more about why is that?
Yeah, these two smaller heat pumps, we have calculated the energy required, that is around 0.13 megawatt, and another is 0.24 megawatt. Based on that electricity consumption, we calculated the energy consumption required, which is very less than the water loop system. And water loop system is a very big heat pump. It has to be heated from 50 to 94 degrees Celsius, and it requires more power. I think it's around 0.15 megawatt, and that gives a more cost or the energy consumption rate than these small heater pumps. And these small heat pumps are integrated with the splitter reboiler and the exchanger, which will require very small modification in the existing plant. So that's why these are cheaper than the other water loop.
The compressor especially, so if you did a heat pump, the compressor is especially less powerful.
Yeah.
And that also makes a difference in cost of the heat pump.
Okay, thank you very much.
Yeah, thank you.
Thank you, Marit and Amar, for your presentation, for your pitch. And the one question, because we still have 8 minutes left and we still have one pitcher digitally tuning in. So I would like to give the floor digitally to Ertan Torun from IBK. If he is... he's already there. Welcome. Nice to see you. You have 8 minutes left. I hope you can hear us loud and clear. And I will help you scrolling down through the presentation.
Okay, thank you very much. And thank you to have the opportunity to introduce myself and my company and the solutions probably for Ducor. I can't see the slide, the first slide. Yes, and this thing. My name is Ertan Torun, account manager at, in the meantime, sales manager at IBK, responsible for the sales and design team of IBK. And we are engineering and producing cooling system for the industrial applications, but also for HVAC applications, standard solutions and tailor-made solutions. Next slide, please. That's the wrong slide, it's the wrong presentation, but I can explain this. This is in Dutch, but what is stated here is that it's more or less our DNA. And we think it's, not only we think, but it's important that we are making sustainable solutions for the industry, but also to have a continuous, and we do this by continuous focusing on innovation and implementing newer systems and getting learning and getting it to a higher level. Next slide, please. This is what we do. And what I earlier mentioned, we have sustainable solutions for our production and climate work systems. We are a small, relatively small company with approximately 40 employees, engineering, service engineers, but also some sales, sales services. We're part of the Sauer Group. Heine Hopman is also a Dutch company, so we are a fully Dutch company. What I only mentioned, engineering, installation, but also maintaining the installation, which is very important because specific for the industrial solutions, the installations will be relatively long, have a long durability from so let's say 20 or sometimes 30 years. And what we are trying to do is to combine the standard and tailor-made solutions because both of them have their benefits. Next slide, please. These are the possible standard solutions. From in the left corner above, we can see the chillers, the standard chillers, the standard heat pumps. On the right side, we have the compact ammonia chillers. On the left underneath, we see the absorption cooling. It's also for the HVAC solution, but also for the industrial solutions and the rooftops on the right side beneath, mostly for distribution centra. Then the next slides. What we can see here are some pictures of some heat pumps, some refrigeration systems for the industry, and tailor-made solutions with a highly focus on high efficiency. What I mentioned is that, next slide please, that we have to focus continuously on innovations, and one of the innovation is nice to mention is a heat pump freeze-con, which we developed together with DNO, and which can dehydrate water from salt and protein solutions, and it will have a follow-up. So it's a very interesting system, where it's possible to improve and to enhance the quality of the products by means of electricity. So no fossil fuels are necessary. And then I will come up to the solution of Ducor, and one of the innovations that we have done in the past years is the high temperature heat pump. But not only the high temperature heat pump, but it also can produce steam. Next slide, please. Now the next slide is no. Back, yes. What you can see here is that we have from let's say 2012, we started with TNO and some other partners by developing a steam producing heat pump, which makes it possible to produce steam, but not only steam, but also superheated water by means of electricity. And as you can see, I will not go into details, but as you can see, it's an ongoing process. And nowadays we have the technical available for such kind of heat pumps. Next slide, please. I will not stand still long for this, but it's the applications are very broad, of course, in the industry, food industry, beverage industry, paper industry, but also the chemical industry. Next slide. So we have let's say three. One moment. Nowadays we are further on developing the heat pumps available for maximum 125 degrees. We're also starting beginning next year, with the Kickstart project, which is a very interesting project with 14 other partners to not only to build the heat pump, but also to implement and to integrate the heat pump, which is very important. And we will continue with the innovation of the 150 degrees steam producing heat pump. And that will bring me to the next slide, where I can have a short and rough estimate solution for Ducor, because we have the technical solution for Ducor. We are convinced that if we have to produce 95 or 90 degrees water, we can do this with a highly COP. It's not a standard solution, and we believe, certainly for the coming years, that the industry is there's a necessity for tailor-made solutions, specifically made for each industry. This one is already made, and it's already we're now at this moment we are putting it into operations and testing it on site, and it's almost for the same applications. And the benefit and advantage of this system is that we integrated extra heat exchangers, and that will bring into Ducor that the extra and the other heat resources and other heat sources can be used to enhance the efficiency of the heat pump. Next slide, please.
You have 22 seconds left.
I will finish.
Oh,
and as you can see, it's how we start. We analyze. First we have to analyze the heat and energy demand. We have to search where the heat source is available. But most important, and that's the most important thing, it's not only about the temperatures, it's also about the demand in time.
The demand in time. Well, thank you so much, Ertan. It was just in time. We don't really have time for questions, but you are stating that you have the right solution for Ducor. I'm curious if compared to other pitches that will be the case. We will see that after our table discussion. Quickly, one question, Rens, or do you know enough?
For now, I know enough.
For now, he knows enough. Then I would like to thank you. Hopefully you can join digitally during the table discussion, and well, fingers crossed if IBK will be the one who Ducor chooses to discuss their business case further with. Well, we're right on schedule, and I would like to present the next speaker. In the meantime, when Rens will be overthinking all the information he just got from the pictures, I would like to ask Robert Geurts to join me on stage and give a short presentation. It will be on industry policy and innovation.
Yes, thank you.
That sounds interesting, so please
thank you.
Go ahead.
So I'll give you some time to think about the pitches and tell you something about what the province of South Holland does on industry and innovation. Let me introduce myself first. I work at Provincie Zuid-Holland, the province of South Holland. I'm the program manager for port and industry. And the fields that I'm active in is the economic policy, energy transition and circular economy, and the nitrogen problems that we have in permitting these times, all focused on the port and industry. My expertises are mechanical engineering, that's what I studied. I have knowledge of fire and industrial safety, energy transition and regional economy. And in the past 20 years I worked in consultancy industry, and already quite a long time in the regional government. All right. Yes, transition in the industry, that's what I'm responsible for at the province. Our policy starting point, or formal policy starting point, is the national and the regional, the Rotterdam climate agreements. That's of course the formal starting point. We also signed the national climate agreement as a province as well. And our policy starts with a regional industry report that we made. I translated it to English. It's got a Dutch title. In 3 steps towards a sustainable industrial cluster. And that's actually the basis for our work these days. And of course, we are, as a province, we are a small player in this very, very complex and large field of energy transition. So cooperation is key to us and to other organizations in this region. Our main goal is a low carbon and circular industry in 2050. Well, that's far away, and we translated that to what do we do today. And I will tell you something about the 3 steps that were defined in the report. Well, the first step that we're aiming at is energy efficiency and infrastructure, which I translate into how to make the current industry as efficient as possible. Second step is energy transition. How do we replace the fossil fuels that are used in the industry by renewable fuels and renewable energy sources, not only fuels, of course. And the third step is the circular transition. How can we replace our fossil feedstock by renewable feedstock? It's a bit slow, I think. Second try. Yes. What do we do? Now, some examples of what we do as a province. In the field of, in the first step, the energy efficiency. For instance, we conducted a large infrastructure study for the entire province, but actually all Dutch provinces conducted the same study. And at a national level, we are combining all the information. So this gives us quite a deep knowledge of the challenges we face in infrastructure development, locally and also nationally. Of course, we didn't do that alone. We did that with the grid operators. We also fund projects. We have an arrangement for infrastructure, a subsidy arrangement for infrastructure between industrial sites. So if you have an opportunity for energy savings and you need infrastructure, well, this could be a possibility for you. We support energy innovation studies, and we also, our more formal role is environmental permitting in the industry. In the energy transition field, we stimulate the use and production of hydrogen. We paid, we're one of the funders of the H-Vision studies, for instance. We support knowledge development and studies. We also support the field lab industrial electrification. And another thing that we do is that we are part of the studies for the landing of offshore wind power. It's called VAWOS, Verkenning Aanlanding Wind op Zee. And that's a typical spatial planning role for us. In the circular transition, we stimulate innovation. For instance, Planet Bio in Delft is already also funded by us. And also we organize the PACT Challenge, we call that. And this is about using waste to create a new feedstock. And we organize access to funding, and I will tell you something about that later, but that's part of my what I want to tell you today. So innovation for us is a very important aspect. In all the things we do, innovation is well, you could say key. And we are the initiator and shareholder of Innovation Quarter. That's a regional development company in this region. We stimulate networks between organizations, between government, knowledge, and companies. For instance, Cleantech Delta, Maritime Delta, Smartport are some of the networks that we finance. We support field labs. I already mentioned FLIE, but the Green Village, RAMLab, Medical Delta are some of the field labs that we also finance. What I say, we fund projects. We have a subsidy arrangement called the Energy and Climate Arrangement, ENK subsidy. IQ handles that for us. And a typical project subsidy is about 30 to 100K per project. And we also organize access to bigger tickets, European funding. I have stated here 3 of them. FLIE and JTF, I will say something about that later. And the React EU call is a call that we held this year, in spring of this year. A total of 7 million was granted to 6 projects in this call. Oh, that was too quick, I think. Something about electrification. Well, it was said already by Josefa. Very important. That's at least what I think. We are moving away from fossil fuels and fossil feedstock. And this part of the Netherlands, Maasvlakte 2, will become an important conversion hub and an import hub for electricity. I've had some pictures here. These are from the consultation in the VAWOS project. And this illustrates that a lot of wind power is landing here in the Rotterdam area in the future. And to handle all this power, infrastructure is needed, of course. We know already from studies that will be quite a challenge. So efficiency and flexibility, especially in the industry, is very important to handle all this energy and to handle the investments as good as possible and as efficient as possible. So the further development of FLIE, like Josefa already stated, is very important, and we want to stimulate and facilitate that. Oh. Yes, okay. It's not going further. Okay, that's all right. I will tell you something about the program Kansen voor West. I've translated it into Opportunities for West, but that's not the formal title. But anyway, this is in English. And the Kansen voor West program is funded by the European Fund for Regional Development, EFRO, and also our national government. And we are now preparing the 3rd call of Kansen voor West. We already had Kansen voor West 1 and 2. And at the moment we're preparing the 3rd call, the 3rd program, I should say. For this region, the province South Holland, 50 million budget is available. And that's the subsidy budget. That's excluding co-funding, this project funding. And it's also excluding additional province funding. So we ourselves add some budget to that as well. This program will be operational from next year until 2027. So for a total period of 6 years. And this budget of 50 million is allocated for 2 priorities. Innovation, the biggest priority, and climate, the smaller priority. Now, this innovation priority focuses on development of key technologies for transition. That's also what we see here today. Further strengthen research and innovation capacity like we do in the field lab. The second priority focuses on climate, contribution on climate change mitigation. So reducing CO2 emissions, renewable energy, efficiency, smart systems, and also transition to circular feedstock. Well, we are now preparing this call with all our regional partners, and if you want more information, you can follow the link that's here. I think the presentations will be shared afterwards. Second call that we are preparing at the moment is the Just Transition Fund. It's a recent fund from the European Community, and it's meant to finance the just transition of industrial regions, especially the CO2-intense regions like the Rotterdam-Rijnmond area. For this area, a budget of almost 60 million is available. And this is allocated for 3 pillars: decarbonizing the existing activities, develop new production chains, sustainable production chains, of course, and further enhance a resilient labor market, or mitigate the drawbacks of the transition in the labor market. The transition plan, the global outline for this fund is finished now. We submitted that to the European Commission, and the next half year they will review it. I will tell you something about that later, about the planning. If you want any more information, contact any of the regional partners or follow the link. I have to say that this link is the link for the consultation. Consultation is already closed, but it gives information anyhow that's useful. So, if you have a project and you think, well, should this Kansen for West, this Opportunities for West Fund, should that be something for me? Should I explore it further? If your project is innovative or contributes to sustainable development, and if one of the 2 other numbers are applicable, if the project aims at more than 30% CO2 reduction compared to your current situation, or in the case of a circular project, has more than 50% reuse of material compared to the current situation, it could be interesting to explore this further. Of course, the quality of the business case is important, because after your subsidy is granted, the realization period is 3 years. And in this subsidy process, there will be a regional policy review, and the typical ticket size of this arrangement is about 500,000 to 2 million. And the maximum subsidy percentage is 50%. So project size, 1 to 4 million and bigger. That's already the size I saw in some projects here, so might be interesting. How's the preparation? Well, the Opportunities for West, Kansen for West, as I told you, the program preparation is finished now. We have a global outline. We are now preparing the first call, the call preparation, with all the details in it. It's not finished yet. And we expect the first call to be open in the spring, in April of 2022. And we are allowed to open 2 calls a year, one in spring, one in autumn. And I'm not sure yet if there will be 2 calls a year, but the coming 6 years, there will probably 1 or 2 calls every year. So this budget of 50 million is spread in a longer period. The JTF timeline. The JTF timeline is not as precise as the Kansen for West timeline, because, like I told you, the program preparation is finished now. Our global outline is ready and submitted to the European Commission. The European Commission will take the next half year to review our plan that we made in the region. And in the meantime, we are preparing to open the call. And we will expect to open our first call in the 3rd quarter of next year. And contrary to Kansen for West, I expect this first call to be quite a large call, because we have to realize this budget. 35% of the budget has to be realized, so project realized already in 2025. So this will not be a series of calls, but I think one large call, and I expect some smaller calls afterwards. So this is my story. Thank you.
Thank you, Robert. Right on time. Any questions? Then I would like to invite you to join us at the table, because of course, we have had some interesting pitches and maybe some projects.
Take a seat myself?
Yeah, you can.
Can I sit here? Thank you.
Take a seat here. Well, this might be interesting if you find a project partner, that there are some subsidies available to get some funding. But, well, Rens, first of all, you have had 4 pitches, 2 digital, and I'm not sure if they are joining us as well.
Yes,
I hope so. Yes, there they are. Welcome, gentlemen. Well, some questions on first ideas, or that you think, hey, that sounds interesting.
Yeah, the pitches really gave good insights and also had a different view on the topic. That was good to see. Maybe first some more detailed questions for the 4 pitches, and then don't know how we will end up, but that we will see then.
Let's see.
Let's first start in the digital channel with Ertan from IBK. Can you tell a little bit more about the uniqueness of your heat pumps, and why would we choose for you as a supplier?
Yes, I can tell you, because nowadays there are many, not many, but there are some companies that can deliver heat pump up to 90 degrees or 95 degrees. What we are doing is to integrate and enhance the efficiency of the heat pump for specific industries. And another reason that I think it's an advantage of IBK heat pump is that we have the knowledge and have the experience in the past years. We can implement that in the new heat pumps, also for the lower temperatures. And we are a full Dutch company, so it's easy to communicate, and it's for some companies it's nice, but it's also possible to do a load test and a fully factory acceptance test in our factory, which gives a better look and feeling what you can expect in your production area. So we think that these things can help you to buy IBK heat pump.
Does that answer your question?
Yeah, sure. Thank you very much.
Okay.
Maybe if there are questions from the audience, then please raise your hands. Then we can also switch to you for questions. For now, I would like to ask René from Blue Terra a question. You had a really interesting insight, also gave quite some insights in our production process that were not directly in the case, but they were, of course, totally correct. Can you tell a little bit more on the integration of heat pumps in an existing production process related to robustness, turn-down ratios, etc.?
Yeah, that's of course an important question, and I think also because what I understood from your case, the reboiler is more a continuous consumer, and the other one is has not 8,000 running hours, but a lot less. So you might have like a different load of the heat pump. Also in our proposal, the second proposal, not the direct heat, but the heat pump, we go for one heat pump because we know the higher temperature has almost 8,000 running hours or even more, but the other one has a lot less. So going for two heat pumps made it higher capex, and also the savings are a bit less because the lower temperature has much less running hours. So you really need to go for a heat pump that has a turn down for probably 50%, 70%. And most new heat pumps do have this opportunity. Sometimes you can even choose for two heat pumps if there is like quite often a different in load. So if you operate not all the three lines together, you can choose for an option with more than one heat pump, which also adds to the reliability, because that's an important item for you as well. So instead of having one big heat pump, you can have two smaller ones, so you can always have steam or hot water available. So in that case, the turn down is in the heat pump itself, because you can choose between 1 or 2 heat pumps running at the same time.
Okay, thank you very much.
Does that answer your question?
Yeah, it does, definitely.
And that's also what Marit shared, of course, during her presentation, that 2 heat pumps might be an option, right?
Yes.
Yeah, but the difference is that 2 heat pumps, in Marit's case, are 2 heat pumps at different temperature levels. And we said you can either go for a big heat pump that supplies the 2 heat levels, or go for 2 like parallel units, so you can choose between the load that's required, but still have this high temperature, as that most of the time is required.
Yeah, but I think that that you can, well, to make clear what our main point was, that we wanted to integrate the condensers with the of the heat pump with the heat exchangers to lower the temperature that you need to produce. I agree that if you make one heat pump of it with different takeouts for depending on what you need, that is a good possibility. But I think that is a matter of further optimizing of the design, since we are now, well, we had very limited information. I apparently misunderstood the case even, so, of misinterpreted the case. So I think at this moment it was more about the concept and the way to show the way of thinking. And I must say, I found it very strong how you started with the heat exchanger as an option. Now we decided not to, because we expected that there was a technical reason why that wasn't possible. But I think at this moment is about concepts and to show how can you reduce the cost of a heat pump design, and then you can. That's also why we think it's important that our combination of SPIE and Ahoy Haskoning is technology independent, so we can design and build and maintain, but we don't need. We are not married to a certain concept. We can look at what is the best concept for the specific situation.
It's interesting that you have a different point of view and you approach it differently. So I'm curious how you will take that into your decision afterwards. You have more questions to one of the other pitchers.
I have one question for Jacob, the digital channel. Jacob, you were stating that heat pumps for direct steam are readily available and proven. That's somewhat different than I what understood from Ertan. Can you elaborate more on that, on how proven is the concept for high temperature steam applications?
Well, do you hear me right now?
Yeah.
Yes.
Yep.
Am I? Yeah, okay. Well, to be honest, I don't know, because the company I was talking to, they told me they could do it, and I said, well, when it's really necessary, let's talk about it, because when you produce steam, you lose your flow, and when you produce, let's say, thermal oil, for example, then you have a return flow. So it's quite a discussion what and how steam would be. But finally, the message is from the compressor that they are manufacturing right now, they can produce direct steam out of the compressor. But that's the message I got. And if I'm allowed to, I want to say some other things, adding to what the other people have said so far about discussion 1, 2, or how many heat pumps you would need. In my presentation, I mentioned 1 heat pump, but in fact, they are 4 or maybe 5 or 6 or whatever. Because the company I'm dealing with, they only make one new invented compressor, which is made for about 1 megawatt of heat output. Depending on the situation, could be less, and the demand or on the location. But that means also that it's very flexible in the way you use it. Otherwise, you should know that the compressor itself and the technology that's around it will be able to have a modulating down to 30%. That means that when the heat pump will do more or less the same, running down to 30% instead of 100%. So it's quite flexible, and it can, let's say, play around with the temperatures and the source and the demand on the plant. Although every change gives a little bit lower COP, it can depend on the actual situation, of course. But that's about it. It's not.
Thank you, Jacob.
It's not the best answer you're looking for, probably, but but the issue of steam was not really a subject of the discussion I had with the producer.
Okay, thank you very much. I would like to thank all pitches here. They gave many insights. Oh,
we have a question.
I think we have some minutes left. So yeah? Also a question from the audience.
Yeah, sorry, same guy again, Marco Kerstein from FMA. I was wondering, I had a question related to the ROI of the return on investment for some of the cases. From Jacob, he mentioned that his business case had a return on investment less than 5 years, but estimated on electricity cost and steam cost. Maybe you can elaborate on that. Is his estimate accurate enough to confirm this return on investment? And from Royal DHV and IBK, I did not catch their return on investment. Is it less than 7 years or less than 5 years? Maybe they too can elaborate on that, what their estimation was.
Maybe first the final question on maybe a payback time. Just a short answer on this one.
Yeah, we only have 2 minutes left, so.
Can I start?
Yep,
yes.
Sure.
Okay. First, we have to say that we have a low-pressure steam heat pump available up since 2014. And regarding the payback time, it's difficult to say this precisely. But we aim at the payback time for approximately 6 years. And but it's not only the payback time, because not the payback time of the heat pump, but we have to take into account all the implementation and the integration, of course.
Okay, so we have below 5 years, 5 or 6 years. Marit?
Well, I think I agree with the last speaker. If you look purely at the cost of the heat pump, then it's no problem. Then you are well below 5 years. But the question is, how many costs do you have from implementation? And you need far more information on the plan to give any reliable estimate on that.
Looking at the time, Blue Terra, what?
Yeah, I think I do not add to this discussion. I think one good thing to mention is there is a very good subsidy available, the SDE++, for producing heat with heat pumps. And it should take into account next to the subsidies on CAPEX that are available sometimes from either the local authorities or the Dutch authorities. So even if this payback time is above 5 years, there are subsidy possibilities which will bring it below this 5 years, and also give some guarantees and stability for the future business case.
If not, the CCS has taken all the SDE++.
But still, it sounds promising, and I think we should end with a positive note.
It should be possible.
That there are opportunities. Rens, I would like to ask you, with all the different pitches and information that you received, that there are some things that are equal, but a lot of different insights and point of views, and well, I think I don't want to be the one in your seat and making a decision, but which pitcher do you want to have a next discussion with? Because of course more details are needed from your side.
Yeah, thank you again. I think for follow-up, I will have more conversations with all of you because the case is, of course, much broader than what we've presented here and much more complex. But although the case was maybe a little bit misunderstood, but anyways, there was a lot of flexibility during the presentation, and I really liked the alternative rearrangement of the process. So for me, the winner of this case would be Royal Haskoning and SPIE.
Congratulations.
Well,
Congratulations.
very honest.
And you were so nervous in the beginning.
Well, yeah, I was sitting here and I was hearing, oh my God.
It's different.
The case is different than I interpreted it. Oh my God, this is going wrong.
Well, you have time to discuss it further. I have to wrap it up. Also for the digital viewers at home, thank you for your attention. And everyone here being present on location, thank you for your attention as well. This is what the field lab electrification does, industrial electrification does. We combine partners and we discuss opportunities, especially opportunities and challenges. If you want to get in touch with us, go to info@flie.nl and send us an email. We would like to take this up with the industry and the technology partners to speeden up the growth of this new green industry. And would like to thank Rens for presenting the case from Ducor. And I would like to thank Robert, of course, for his presentation and the pictures today. And, well, again, congratulations for winning this pitch.
Thank you.
Thank you.
Thank you all, and see you next time.
Yeah.
Well, my friends, the time has come to raise the roof and have some fun.